How to Find a Habitable Planet by James Kasting is an engaging and comprehensive exploration of the search for life beyond Earth. The book delves into the scientific principles, methods, and cutting-edge technologies used to identify potentially habitable worlds, offering readers a thorough understanding of the factors that make a planet suitable for life as we know it. Kasting, a renowned planetary scientist, guides readers through the fascinating history of astronomical thought, the evolution of Earth's climate, and the groundbreaking techniques employed in the quest for extraterrestrial life. The concept of the habitable zone. The habitable zone, also known as the Goldilocks zone, is a central concept in the search for life-sustaining planets. This zone refers to the range of distances from a star where a planet could potentially support liquid water on its surface, which is considered a critical requirement for life as we know it. Kasting emphasizes the importance of liquid water, explaining that it serves as a powerful solvent for the complex, carbon-containing compounds that make up living organisms, allowing for the necessary chemical reactions to occur. Additionally, water's high heat capacity helps create stable, life-supporting planetary environments by moderating temperature fluctuations. Earth's climate evolution and the faint young sun paradox. To understand the potential habitability of other worlds, Kasting examines Earth's long-term climate stability and the factors that have kept our planet habitable for billions of years. He introduces the faint young sun paradox, which arises from the observation that the sun's luminosity has increased by about 30% since its formation 4.6 billion years ago. This means that the early Earth should have been significantly colder and perhaps even frozen. However, geological evidence indicates that liquid water and life have been present on Earth for at least 3.5 billion years, far longer than expected based on the sun's evolution alone. Kasting proposes that higher concentrations of greenhouse gases, particularly carbon dioxide, CO2, and possibly methane, CH4, played a crucial role in warming the early Earth. He describes the carbonate-silicate cycle, a negative feedback loop that helps stabilize Earth's climate over long timescales by regulating atmospheric CO2 levels. As the climate warms, silicate weathering rates increase, drawing down CO2 and cooling the planet. Conversely, when the climate cools, weathering rates slow down, allowing CO2 to accumulate and warm the planet. This negative feedback mechanism has helped maintain Earth's climate within a habitable range for billions of years. The rise of atmospheric oxygen and its impact on climate. Kasting explores the rise of atmospheric oxygen and its impact on Earth's climate. Geologic evidence suggests that oxygen levels were very low during the first half of Earth's history, likely due to the absence of oxygen-producing cyanobacteria. The eventual rise of oxygen, which occurred around 2.4 billion years ago in the Great Oxidation Event, GOE, had profound consequences for the Earth's atmosphere and biosphere. Kasting argues that the GOE may have triggered the Paleoproterozoic glaciation, a global ice age, by reducing atmospheric methane concentrations. Methane, a potent greenhouse gas, is readily oxidized by free oxygen, and its removal would have led to a significant cooling effect. Snowball Earth and climate instability. The book delves into the concept of runaway glaciation and the Snowball Earth hypothesis, which suggests that the entire Earth may have been covered in ice during several periods in its history, specifically during the Neoproterozoic era around 720 to 635 million years ago. Kasting explains the ice albedo feedback loop, a positive feedback mechanism that can destabilize the climate system and lead to global glaciation. As ice sheets expand, they reflect more sunlight, cooling the planet further and allowing even more ice to accumulate. This positive feedback loop can cause the climate to rapidly transition from a relatively warm state to a completely ice-covered one. Kasting presents evidence for low-latitude glaciation during the Neoproterozoic era, which strongly supports the snowball Earth hypothesis. He discusses the challenges of explaining how photosynthetic life survived these global glaciations and considers possible mechanisms, such as the existence of small pockets of open water or a soft snowball scenario with thin sea ice. The implications of snowball Earth events for the evolution of complex life are also explored, as these extreme glaciations may have served as evolutionary bottlenecks, creating opportunities for new forms of life to emerge in their wake. The inner edge of the habitable zone, Venus as a case study. Kasting uses Venus as a case study to explore the inner edge of the habitable zone around the Sun. Venus has a surface temperature of 460 degrees Celsius, 860 degrees Fahrenheit, and an atmosphere composed primarily of CO2, with a surface pressure 90 times that of Earth. These hellish conditions are the result of a runaway greenhouse effect, which Kasting argues may have been triggered by the loss of Venus's water over time. According to his model, Venus may have started with Earth-like water inventories. But as the Sun's luminosity increased, the planet's surface temperature rose, causing its oceans to evaporate. The water vapour then made its way into the upper atmosphere, where it was broken apart by ultraviolet radiation. The hydrogen atoms escaped to space, while the oxygen atoms reacted with the planet's crust. This process, known as the runaway greenhouse, led to the complete loss of Venus's water and the development of its current hostile environment. Kasting estimates that the inner edge of the habitable zone lies at approximately 0.95 astronomical units, AU, from the Sun, just inside Earth's orbit at 1 AU. This implies that Earth is perilously close to the inner edge of the habitable zone, and that a relatively small increase in solar luminosity or atmospheric greenhouse gas concentrations could push our planet into a runaway greenhouse state similar to that of Venus. This knowledge has important implications for the search for habitable planets around other stars, suggesting that planets orbiting too close to their host stars are unlikely to retain liquid water on their surfaces. The Martian Climate Puzzle. Mars, the fourth planet from the Sun, presents a different challenge in the search for habitable worlds. Mars's surface is currently cold and dry, with a thin atmosphere composed primarily of CO2. However, there is abundant evidence that liquid water flowed on Mars's surface in the distant past, raising questions about the planet's climate history and its potential for habitability. Kasting discusses the geomorphological evidence for past water on Mars, including the presence of large outflow channels, valley networks, and sedimentary deposits that resemble those formed by rivers and lakes on Earth. The book examines the various mechanisms proposed to explain the apparent warmth and wetness of early Mars, such as increased atmospheric CO2 levels, the presence of other greenhouse gases like sulfur dioxide SO2, and the formation of CO2 ice clouds. The book examines the various mechanisms proposed to explain the apparent warmth and wetness of early Mars, such as increased atmospheric CO2 levels, the presence of other greenhouse gases like sulfur dioxide SO2, and the formation of CO2 ice clouds. Kasting notes the challenges in producing mean surface temperatures above freezing, even with high CO2 levels, due to the formation of CO2 ice clouds that reflect sunlight and cool the planet. He also addresses the absence of carbonate rocks on Mars's surface, which poses a challenge to models invoking high CO2 levels to warm the planet, and suggests that acidic conditions may have prevented their formation or led to their dissolution. Detecting habitable planets, methods and technologies. In the second part of the book, Kasting explores the methods and technologies that scientists are developing to detect and characterize potentially habitable planets around other stars. He discusses the radial velocity technique, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. This method has been used to discover hundreds of exoplanets, revolutionizing our understanding of planetary systems. However, detecting the tiny wobble caused by an Earth-like planet is incredibly challenging, requiring a precision of just a few meters per second. Another powerful technique for finding exoplanets is the transit method, which looks for the tiny dip in a star's brightness that occurs when a planet passes in front of it. The Kepler Space Telescope has used this method to discover thousands of exoplanets, including many that are similar in size to Earth. The transit method not only reveals the presence of a planet, but also provides information about its size and orbit, which is crucial for determining whether a planet might be habitable. Kasting explores the concept of the habitable zone in more detail, discussing the range of distances from a star where a planet could potentially support liquid water on its surface. The habitable zone is a useful guide for narrowing down the search for potentially habitable worlds, but it's not a guarantee of habitability, as many other factors, such as a planet's atmosphere and geological activity, play a crucial role in determining whether a world can support life. Direct imaging and biosignatures. The book also discusses the challenges of directly imaging exoplanets, which involves blocking out the overwhelming glare of the star to see the faint light reflected by the planet. This requires incredibly precise optics and advanced coronagraphs to block out the star's light. While direct imaging is still in its infancy, it holds great promise for studying the atmospheres of exoplanets and searching for signs of life. One of the most exciting prospects for direct imaging is the possibility of detecting biosignatures, or signs of life, in the atmospheres of exoplanets. For example, the presence of oxygen in a planet's atmosphere could be a strong indication of photosynthetic life, as oxygen is a highly reactive gas that would quickly disappear without a constant source. Other potential biosignatures include methane, which can be produced by certain microbes, and the combination of oxygen and methane, which would be a strong indication of a biologically active world. Other types of habitable worlds. Kasting explores the possibility of finding other types of habitable worlds, such as moons orbiting giant planets, or even rogue planets that have been ejected from their star systems. These worlds may not fit our traditional definition of a habitable planet, but they could still harbour life in unexpected ways. For example, Jupiter's moon Europa is thought to have a vast ocean of liquid water beneath its icy surface, kept warm by tidal heating from Jupiter's gravitational pull. This subsurface ocean could potentially support microbial life, even though Europa's surface is far too cold for liquid water. The future of exoplanet research. The book concludes by looking to the future of exoplanet research and the exciting possibilities that lie ahead. Kasting discusses the next generation of telescopes and instruments being developed to search for habitable worlds, such as the James Webb Space Telescope and the 30-metre telescope. These instruments will allow us to study exoplanets in unprecedented detail, searching for signs of life and potentially even detecting the presence of civilizations on other worlds. The search for habitable planets is a grand adventure that pushes the boundaries of human knowledge and technology. It requires the combined efforts of scientists, engineers, and visionaries from around the world, all working together towards a common goal. It's a journey that will take us to the farthest reaches of the universe and challenge us to think beyond our own world and our own existence. Conclusion: How to Find a Habitable Planet provides a comprehensive and engaging overview of the scientific quest to understand the conditions necessary for life beyond Earth. Kasting's work highlights the importance of interdisciplinary collaboration, drawing upon insights from astronomy, geology, biology, and atmospheric science to paint a holistic picture of planetary habitability. The book emphasizes the critical role of Earth's long-term climate stability in maintaining habitable conditions and the delicate balance of factors that have allowed life to flourish on our planet for billions of years. By studying Earth's climate evolution and the mechanisms that have kept it within the habitable range, such as the carbonate-silicate cycle and the rise of atmospheric oxygen, we gain valuable insights into the potential for life on other worlds. Kasting's exploration of the inner and outer edges of the habitable zone around the Sun provides a framework for understanding the limits of planetary habitability and guiding the search for Earth-like planets around other stars. The fate of Venus serves as a cautionary tale, illustrating the consequences of a runaway greenhouse effect, while Mars demonstrates the challenges of maintaining a warm and wet climate on a smaller planet with a thin atmosphere. Throughout the book, Kasting presents complex scientific concepts in an accessible and engaging manner, using real-world examples and analogies to clarify key ideas. He compares the carbonate-silicate cycle to a thermostat, automatically adjusting Earth's temperature by regulating atmospheric CO2 levels, and likens snowball Earth events to a hard reset of the Earth's climate system. The search for habitable planets is not just a scientific curiosity, it has profound implications for our understanding of our place in the universe. If we find evidence of life on another world, it would be one of the most significant discoveries in human history, suggesting that life is not unique to Earth. On the other hand, if we search far and wide and find no evidence of life beyond Earth, it would suggest that life is incredibly rare and precious. In conclusion, How to Find a Habitable Planet is an invaluable resource for anyone interested in the search for extraterrestrial life and the fundamental question of what makes a planet suitable for life. Kasting's book lays the foundation for understanding the scientific principles and methods behind this quest, while also providing a tantalizing glimpse into the possibilities that await us as we continue to explore the cosmos. It is a must-read for students, researchers, and enthusiasts alike, offering a comprehensive and engaging introduction to one of the most exciting and rapidly evolving fields of modern science.